The question is, what are the basic steps in calculating the values of the shear force B and the bending moment M at a point in a beam? I'll answer this question with reference to this problem, which is a typical beam problem. We have a cantilever beam that is fixed at point B and subjected to a point load and a uniformly distributed load. We are interested in calculating the shear force V and the bending moment M at a certain point in the beam. Normally, the first step would be to determine values for the support reactions. This has been covered elsewhere, so I will not spend too much time here. Keep in mind that in some problems like this one, it may not be necessary to determine support reactions to find internal forces. However, having values for support reactions would allow you to double check your calculations. These statements will become meaningful to you as I go through the remaining steps here. Step 2. Section the beam at the point where the internal forces are to be calculated. Separate the beam into two parts, choose a part to work with, and complete the free body diagram for that part. Say I'm interested in calculating the internal forces at point D in this particular example. Then you section the beam at point D like shown here, separate it into two parts, the left part and the right part. Since the same three internal forces, ND, MD and VD, act on both sides, you only have to use one side in the analysis. Supposing, say, I choose to use the left side. Then just for the purpose of calculating the internal forces, you only have to complete the free body diagram for the left side. And you can see there are no supports on the left side, and therefore there's no need to find the support reactions in order to find these internal forces. But once you find values for the internal forces using the left side, you can check whether your calculations are right or wrong by using the right side. For that purpose, you need to find the support reactions and complete the free body diagram for the right side. Anyway, let's talk a little bit more about the internal forces at point D for a beam like this. Here we are talking about 2D problems, meaning everything happens on this plane, the XY plane. X here is the horizontal coordinate axis, Y is the vertical coordinate axis. So all of the forces and the boundary conditions and everything are on this plane, XY plane. So for a 2D problem like this, these are the three internal forces that could exist at point D. The axial force ND, the shear force BD, and a bending moment MD. The magnitudes of these internal forces are equal to each other and the directions are opposite. The arrows for these forces have been drawn in accordance with the sign convention. This is the sign convention we will use here. The tensile axial force is positive. Taking the x-axis as marked in this picture as positive, considering the left side, these are the positive directions for the shear force and the bending moment. Shear force is marked vertically down on the left side, and the bending moment is marked counterclockwise on the left side. And of course, on the right side, the directions will switch. The shear force acts vertically up, and the bending moment acts clockwise. Here is an exaggerated version of this point right there, point D. For generality, we always mark an axial force like I have done here. You will find that in most beam problems, the axial force is 0. But not in all problems though. There could be a horizontal or an inclined externally applied force which might give rise to a horizontal axial force. So to be on the safe side, you're going to mark an axial force, and if it is in fact 0, you use the equilibrium equation to show, like the procedure you're going to follow in step 3 right now. Alright, our third step is to write down the equilibrium equations for the site we have selected for further analysis and evaluate the internal forces. In this example, we have selected the left side, right? So there are three internal forces, ND, MD and V sub D. And we need three equations, and these are the three equations for evaluating these three forces. Sum of the forces in the horizontal direction, and only force we have acting in the horizontal direction on this free body diagram is ND, and therefore ND must be equal to 0. Sum of the forces in the vertical direction must be 0. In the vertical direction, we have V sub D going vertically down, so that goes in as a negative term. And 2 kilonewton acts in the vertically downward direction, so that goes in as a negative term as well. So this equation leads to a value of minus 2 kilonewton for VD. Now we go ahead and take a moment about one of the convenient points. It could be point A or point D. So here I have selected to write down the moment equilibrium equation about point D. So MD is acting counterclockwise, and that's the direction that I have chosen for the equation. In other words, if there is a moment that acts in the counterclockwise direction, that's going to go in as a positive term in this equation. So MD goes in as a positive term. 2 multiplied by 1 meter goes in as a positive term as well. So that gives you a value of minus 2 kilonewton meter for MD. So you can see I didn't have to evaluate the support reactions at point B in order to do this, and also I didn't have to use the right side at all in order to evaluate these values, right? But we'll use the right side to check our values like I will do right now. So here they are. Basically what I'm doing is I'm writing down the 3 equilibrium equations for the right side, and then using the values we got for the internal forces in part A, I'm trying to see if the sum of these quantities work out to be 0. For example, in the first step right here, I'm summing up the forces in the horizontal direction, right? So if I were to use the value for ND that I got in part A, which is 0, right, it should sum up to 0, and it does. And therefore, my equilibrium equation for the right side is satisfied using the values I got in part A. And similarly, in this line right here, you're summing up the forces in the vertical direction, right? So you got this VD plus 5 minus 3. But now I'm going to use minus 2 kilonewton for V sub D, which is what we got in part A. And if I use that, and you can see this sum works out to be equal to 0, and therefore the equilibrium equation is satisfied using the values we got in part A, and so on, right? So you can follow this line, the moment equilibrium line, easily. Now you can say that the values you got for the internal forces in part A are consistent. So to sum, this is how you find the internal forces at a point on a beam.